next up is our sponsor presenting Automation in Flight Software by Jonathan Brandenburg and Zach Metzinger.
Very nicely done. Thank you very much. First of all, how's my audio? Real quick. Okay. I tend to be loud, but I tend to be fast, so slow me down if I need to be. Thank you very much for once again allowing us to sponsor Flight Software Workshop this year. We're very excited to do that. We'll be giving two different presentations today, two short ones, so you get two for the price of one. One is a brief discussion of automation in flight software and some of the advancing technologies that I know we've all heard about, and the second will be on optical communications platforms. So my name is Jonathan Brandenburg, as we've already noted. I work for a company called Medix out of Houston. We do flight software, robotics, multi-body dynamics, simulation, digital twin, VR, AR, all sorts of exciting stuff. My part of this puzzle is in the flight software realm. It's something that I'm very excited about, and I have the opportunity to work with both commercial and non-commercial clients. And that breadth of experience in both crewed and uncrewed space systems has really fed into a lot of the work that we're doing and what we're talking about today in terms of flight automation. But I'm going to first talk about kind of what do I mean by automation. I'm not talking about automated unit testing. I'm not talking about code generation, although those are very interesting aspects. I'm really thinking more of, well, thinking machines, right? Machines that act on their own, autonomy. They act autonomously. And I realize that, you know, for those of us that are science fiction fans, the idea of autonomous machines may bring to mind things like, you know, HAL 9000 or Skynet, or, and here's a blast from the past, Colossus, if you're into 1970s science fiction, so look that one up if you like. But those are examples of what happens when automation goes wrong, in a manner of speaking, right? When autonomy goes to unexpected regions or unexpected directions. And that's really what we want to be concerned about today when we're talking about autonomy. And I'm going to deal with this in a roadmap fashion. I'm going to start by talking about something that we're very likely already very familiar with in this realm, which is fault determination, isolation, and recovery. And at its simplest, and I don't mean to downplay the complexity, I'll speak to that in a moment, but at its simplest, this is really an if-then-else, right? If you think about it, if the voltage on my Fox satellite that I had the pleasure of working with in the amateur radio world, if that voltage drops below a certain threshold, then go into safe mode, start shedding load. Very, very simple. You detect a failure and you figure out what to do based upon that failure, and you take that action. But that simplifies it a lot, right? You have situations where you can have degradation of sensors or systems as opposed to outright failures. You have situations where you have a single failure maybe reflected across multiple sensors. Those are the kinds of things that make this very complex. And then if you start wanting to deal with multi-failure modes, then your complexity has gone, I think exponential is really a fair term to use here. So the idea is that this can get very complex, and it fundamentally falls to humans, us, to build these fault determination and isolation recovery tables, these tables that determine actions. And humans are fallible. We do make mistakes. Now, hopefully not very often, and hopefully we have a lot of reviews on our work, but we are humans, and humans do make mistakes. And I want to keep that in the back of our mind. Humans aren't perfect. And then that brings me to my next level of autonomy, I guess, which is autonomous maneuvering. The chart that you see here, which I know you absolutely cannot read, is a conjunction chart from SpaceTrack. These are satellite conjunction events when satellites are getting within a certain range of each other. And I was intrigued when I stumbled across this story about autonomous maneuvering by the Starlink satellites by SpaceX. Now, I first have to say I don't have any inside track on SpaceX, and I don't have any inside information, but I did look at the FCC filings, and I found it truly fascinating that SpaceX Starlink satellites made 24,000 autonomous maneuvers in just the last half of 2023. Now, I don't know what they mean by autonomous, right? According to their filings, they maneuver their satellites if there's a greater than a 1 in 100,000 chance of collision with another space piece of debris or functioning satellite. And that's a pretty conservative viewpoint. But the real question is, where does that autonomy lie? Are they doing orbit propagation on their satellite and calculating conjunction events? Maybe not. Are they doing conjunction analysis on the ground and then uploading and then letting the satellites autonomously fire? Possibly, probably, in fact. And if somebody here knows the answer, I'd love to see that in the chat. But the idea here is 24,000 of anything is a big number. And it seems extremely unlikely that a human can be involved in every single one of those. So when they say autonomous, they truly do mean, I have to believe, autonomous in most circumstances. I could see a situation, though, where if there were some exceptional events or a scenario that hasn't been seen before or a multi-body conjunction event, which as far as I know is hypothetical, those kinds of things could probably require human intervention. And so I had this idea that when you have autonomy at scale, you're going to have a lot of things done without human intervention, but then there's going to be these exceptional circumstances. Maybe you put up guardrails in the automation. And that's where I think the second point that I want to bring up is not only human fallibility, but the idea of guardrails around automated systems are both key points that we could keep in mind. And that finally brings me to my final topic, which is artificial intelligence. Yes, you can check that off your buzzword bingo. I did get it in my presentation today. But while artificial intelligence is a buzzword and it's a little hyped, that simply means that it's becoming more mainstream in a lot of respects. In fact, we have a lot of autonomous presentations at this conference, this workshop. And I didn't specifically see, but I would imagine we have some artificial intelligence applications as well. And I know we're seeing many of these announced by our partners and competitors. But the idea really comes down to when can we trust artificial intelligence? Well, I'm not talking about large language models or generative AI. That seems a little close to asking the internet to operate your satellite, and doesn't sound positive at all. But I'm more thinking about the convolutional neural networks where we're training classification systems. And then that brings to mind, I mentioned earlier that Medics is into simulations and digital twins. And the idea of training these neural networks, these deep learning systems on simulated data provides a lot of value toward operating your satellite, potentially classifying behaviors. And then that leads to the question of, can I trust it? Can I trust it when there's a human on my space station that's running my machine learning algorithm, my deep learning classification network? And how do you answer that? I mean, I guess one way to answer that would be, well, I'll trust an automated system when it's at least as good as a human, or maybe 10 times as good as a human. And then that brings me to a colleague of mine. My nephew actually works for a large insurance company, and he's been tasked with putting together insurance products for the autonomous trucks going onto public Texas roads here real soon now. And they asked the question, really, same question I just asked, how good does the autonomous truck have to be? And the answer is at least as good as a human or a lot better than a human. That naturally led to the question of how good is a human? And it turns out there's surprisingly little information on that. So what they ended up doing is they went to traffic cameras, primarily in California, because there's a lot of traffic cameras. And they built simulated environments using close calls, near misses, and accidents that they caught on those cameras. And then they put the truck in those same scenarios. And they determined how the truck would react and whether it did at least as well as a human in avoiding that accident. So that's a story, an anecdote, I guess, that I think can be applicable to some extent in our industry as well, which is how do we get to a point where we can trust artificial intelligence algorithms? When do we accept the fact that humans aren't perfect either, and somehow put guardrails either on the input or the output of a neural network or an AI type system and allow it to function? And that's the kind of research we've been doing. I don't have a lot of time to talk about it right now, but I do encourage you to stop by our booth out and ask me questions, and I'll answer as best I can. In the meantime, I'd like to turn this over to my colleague, Zach Metzinger, to speak about optical communications. Zach, take it away.
All right, thank you, Jonathan, and thank you all for being here today. If I get my timer running just to make sure. Oh, he's got one here for me. Excellent. That barbecue was fantastic. Who agrees with me? Good barbecue? Oh, I think it was great. As Jonathan said, my name is Zach Metzinger, and I work with him at Medix. We are actually out of Dallas. Medix is based out of Houston, Texas. We do, for our civil contract work on the Lunar Gateway program, and we also do things in the commercial space, like optical communications. So optical communications is becoming a fairly big thing. It's becoming something that everyone wants to do. There's a lot of interest. And why would you want to do optical? There are a couple of characteristics of optical communication that are really attractive. Number one, primarily bandwidth. There's just a limited amount of RF spectrum available for downlinks. We're already seeing where S-band downlinks are being de-emphasized or even not even granted for licensing, having to go up to X-band, Ku-band, Ka-band, and beyond into millimeter wave. And as you reach those higher frequencies, you have different challenges, more difficult challenges, and the slice of spectrum that you have is much smaller. So you get maybe 100 megabit a second downlink. You can go a little bit higher than that, but that's kind of what everybody's shooting for right now. If we're talking about space lasers, you can go to optical. Anybody get that, lasers? No? Nobody? Okay, all right, never mind. Nobody here likes Austin Powers. With the optical, we can see in deep space was demonstrated 267 megabit at 31 million kilometers, and up past 200 gigabit a second in LEO orbit. And I'm talking about two programs we'll talk about in just the next slide here, but those sorts of transfer rates are extremely important for data gathering missions, where you're potentially sending down gigabytes of data from exploratory missions to the ground. The second characteristic that's important is regulatory. Right now, optical is fairly unregulated. The ground stations actually have the most regulation because you're near people, and if you happen to be pointed near the horizon, you could potentially get some scatter off the atmosphere, scatter off objects, and damage someone's vision on the ground. But once you're in orbit, by the time the laser reaches the ground, it's fairly diffuse. You don't have to worry too much about it. So the licensing is typically local and not an FCC sort of regulatory action. Finally, confidentiality. So you've got a small collimated beam, and that means for at least commercial interests, you can keep things fairly secure, even if your data link is encrypted. Encryption systems have been broken, people implement them poorly, and sometimes you just don't want to have anybody know you're talking across a laser link, and this is the way to do it. Talk about a few selected adopters, NASA JPL. Isn't it great? I got to go right after the Psyche guys. So thank you very much for showing that picture of the laser going from the observatory up to toward the satellite. Their program is, or their experiment was DSOC, not DSCO. I really hope that you'd make it into DISCO. That would have been a really cool acronym, but it's actually DSOC. That's on Psyche, and that's the one that did the 231 megabit per second. We also had an earlier experiment on the ISS, the OPALs, that was a little slower, but that was certainly a lot earlier in optical communication. That was back in 2014. SpaceX is a very heavy optical network, and I actually have a quick, I think it's 9,000 data links. So they have 9,000 lasers in their constellation, and they transmit 42 million gigabyte per day across their inter-satellite laser links. And what that allows them to do is it preserves that RF spectrum for consumers and uplink. It also allows them to extend their network across areas where they may not have any land. So if you happen to be in, let's say, Bora Bora, and you want to get data over there, you want to get somebody who has internet over there, you can go up RF across the lasers and then back down RF. And it really allows you to have a full mesh across the entire globe, which is something like 70% water. So there's a lot more water than there is land. Finally, DARPA is getting into this as well with what they call their Space Bacon, which is their space-based adaptive communication network. And they're looking at it from defense. They're looking at it from interoperability. I believe Telesat just got the contract for their interoperable terminals. But everyone wants to get into the optical communication market. So that leads us to what Medix has been doing, and we want to jump into this as well. So this is a shot of Neil, one of our engineers, really smart guy working inside of an optical table. And this is some of our phase 1 work where we're working on the hard problems with lasers. You might look at, you might say that optical path alignment, oh, it's great, it's easy, you just point 2 lasers at each other. Well, depending on the size of your beam, that can be actually incredibly difficult, even if they're stationary. Now, imagine something in LEO orbit, where you might only have 12 minutes as that satellite goes across. You've got to accurately hit the target and establish a link and then maintain that for 12 minutes as it's going over, and you've got clouds or anything else in the way. It's actually a very difficult problem. It's something that can be solved with the right amount of work. Inside of our optical table, we've actually got the ability to do some environment simulations. So just sheer path loss, you might just, the amount of distance that you have to cover with a laser, the absorption of the atmosphere, we can simulate that with neutral density filters. We can simulate the refractive index of air that's heated in different areas, so with scintillation effect. You've seen this with mirage across the desert, for instance. And finally, obstructions. So you'll see clouds go by all the time, and that's one of the main impediments to a laser comm system is the cloud obscuring effect of clouds. Neil can actually simulate that with a vaporizer system that he has in here that can pump in various densities of clouds and shoot the laser through that and see if we still maintain our link and our error budget. Some of the things that we came across when we were doing our phase 1 experiments that really surprised us is no one thinks about operator safety. Everybody knows about RF safety. Don't stand in front of the antenna. It's going to microwave your eyeballs out. Well, you get the same thing with this infrared laser, which typically a space to ground link would use a 1550 nanometer laser, and that is invisible, so you can't see it. And when you're dealing with greater than 1 watt of power coming out of an erbium doped fiber amplifier, you can have permanent eye damage faster than you can react. And since you can't see it, you don't think to blink. And that's why Neil's got his safety glasses on, and he's got the interlock system actually bypassed at this point, doing some alignment in this box. So all of these things are areas that we're getting into that the phase 1 experiments were very eye-opening, very refreshing to get into this area of research, but y'all are probably interested in the software behind it. So being flight software, how do you deal with this software and hardware design that goes over lasers instead of RF comms? Well, RF is fairly low bandwidth when you consider the comparison of RF to laser comms. So we're looking at a high bandwidth system with error correction. We're looking at active pointing, and we want it to be low power. So you've got a whole bunch of factors that you have to balance. We are trying to use COTS hardware, or common off-the-shelf hardware. That includes FPGAs, that includes optical transceivers. Fortunately, the telecom industry, the datacom industry has produced these transceivers that are off the shelf and have fantastic performance. The MIT Lincoln Labs folks, I know there are a couple here, their T-Bird project was really the inspiration for us getting into this. Watching that, the performance of that was impressive, and we said, hey, we need to do this too. There are challenges with the software, with controlling servos and actuators, as well as delay-tolerant networking. So you have variable delays, just like an RF system, but you have a high bandwidth latency issue, kind of depending on where you're going. So if you're going deep space, you've got more of a latency issue. If you've got a LEO satellite, you've got more of a high bandwidth situation there. So all to say that in the future, I think that we're going to see a lot more of this optical communication, and we're going to have to deal with it as flight software engineers. And it really opens up the conveyance of a lot more information from the sky to the ground, but it does present its own technical challenges, and there's some innovative ways to deal with those challenges. With that, I think we'll move on to the question period. I know that the previous one went a little bit long. We tried to integrate in this last picture here the two things we're talking about. So we asked AI to generate us an AI man being disintegrated by lasers.
Do we have any questions we can answer right now? We have at least one.
Yeah, there is one online, maybe for Jonathan. Are these space programs flying trusted AIs?
Are there space programs flying trusted AIs? I will say sort of in answer to that question, which is a very ambivalent answer. I'm not sure that I'm aware of any that are being used in what I'll call safety critical operations, but behind the classified curtain, there certainly could be. Most of what I'm seeing in terms of AI right now is in what I'll call the sensor package or the payload package, not, say, a safety critical system where humans or the entire mission itself would fail. So I think the answer is sort of.
This may be a bit of a silly question. I'm kind of new to the optical communications, but you're talking about the risk of, refraction hitting people's eyes, something like that. What about like planes, right? That seems like these lasers could be a big issue with planes.
It could be. Fortunately, planes are a pretty small target.
Right.
So, and a lot of you can coordinate that. That can be part of your software solution as well. So let's say you've got the data from the FAA, from transponder data, or the secondary target information is really what they call that. You can interrupt your beam as the airplane is going through a safety box, and then resume it when that is out of the way. It's much like when you have a launch. You have a box that delineates a safety area that you can't have any airplanes in. You just shut the laser off, and then you resume when the airplane's gone by.
Thank you.
Other questions?
Go ahead.
No? Thank you. Please see them at their desk outside. Jonathan and Zach, thank you so much.
Thank you all very much. We appreciate it.